Hello students, in this video we are going to start the first lecture of our syllabus, that is gravitation. So look at the animation. The apple is falling and we all know that Sir Newton discovered the gravitation from that. But he wondered why the apple is falling vertically downward, why it does not fall horizontally or making any angle with the earth surface, right? So his conclusion was as earth is spherical and all the objects falling on the earth are falling vertically downward, there must be some force. There must be some force which is attracting the objects towards the center of earth, toward the center of the earth. Because if the force is from any point of the earth, say this point, then the object from this side will fall vertically downward, but object from this side cannot fall vertically downward. So as the earth is spherical and objects are falling vertically downward, making 90 degree, that is perpendicularly on the earth's surface, there must be some force acting from center of the earth. Now the next point is circular motion and centripetal force. Look at the diagram. The person is holding a string to which a stone or ball is tied and she is revolving it. Its motion will be like this. So this is the motion of the object along the circular path, right? So this is called as circular motion. And as she is pulling that stone or ball towards the center of the circle, means she is applying force towards it, and because of the force applied by the person, the ball is revolving around the circle, right? Look at this diagram. This shows the object which is in the circular motion and its velocity at the instant. So the green arrow shows the direction of the object at any instant or any point, and this orange arrow shows the direction of the force applied by that person, which is towards the center. And we all know that we have studied it in the 9th standard that the object has tangential velocity at the instant. So this diagram shows the tangential velocity of the object at any instant, but it is bound towards the center because of this force shown by orange arrow. This is just for understanding. So the understanding the tangential velocity of the object at any instant. Look at the player. She is giving circular motion. She is first to that object, right? She is holding the object. She is giving the circular motion for the object, and in that motion she throws that object and it will go in straight direction, right? So this is the simple example of tangential velocity of the object. To throw that object in straight direction, she gives it circular motion first, then throws it, right? So tangential velocity of the object in circular motion, we understand it from this, right? So in the previous slide where we studied, where we saw that the person is holding string, if that person lowers the force or the string is cut, what will happen? The ball will go straight, the ball will go in the straight direction where it is cut or where the force is lowered, right? So the force stops acting if we release the string. If we release the string, means we are lowering the force, right? And the stone will fly off along a straight line which is tangent to the circle at the position of the object where the string is release, because that is the direction of velocity at that instant of time. So where the force is, the string is released, at which point the force is the string is released, from that point the ball or that stone will go in straight direction. So we have seen some examples to understand that, right? So it is simple. And so the force acting on the object in the circular motion, which is towards the center, we have seen in that example that the person was holding the string, and because of that force applied by the person in the center, the object was performing circular motion. But when she releases the string, when she lowers the force, the object stops to revolve, right? Stops its circular motion. So that force which bound it towards the center, the force applied by that person, that is called as centripetal force. Let us see the definition. A force acts on any object moving along a circle in circular motion. It is directed towards the center of circle. This is called as centripetal force. The object which is in circular motion, a force always acts on that object which is in circular motion, that is towards the center, that is centripetal force. Centripetal means center seeking, towards the center, going towards the center. Okay, for the moon to go around the earth, there must, for example, we know that moon is revolving around the earth, right? So and this is also circular motion, so there must be some centripetal force at circular motion. If there is circular motion, there must be centripetal force. So as moon is revolving around the earth, means there must be some centripetal force. So that centripetal force here, it is gravitational force acted by earth on the moon. Getting it? Similarly, the sun must be attracting the planets including earth and towards itself. So we know the solar system where sun is at the center and all the planets are revolving in different orbits around the sun, right? So there must be, the sun is also attracting the planets by gravitation force, which acts as centripetal force for the circular motion of the planet. Okay, next. So to study next points, we need to study one geometrical shape, that is ellipse. You can see the shape, it is not like circle, it is like oval shape, right? So let us see the features of properties of ellipse. As we know, the circle has the center, it has a radius which is same to all the points. The distance of the circumference from the center is same. But here in ellipse, we have this, so this large line is called as major axis and this one is minor axis, and this F1 is one focus, F2 is another focus, right? The circle has one center, here the ellipse has two foci, one F1 one focus, second focus F2, and the plural F1 and F2 are the two foci. Okay. If the cone, look at this diagram, if the cone, you can make the cone of the paper, and then if you cut it horizontally, you will get the shape of circle, you will get the circle. But if you cut it slantingly, you will get the ellipse. You can try it. So next we are going to see Kepler's laws of planetary motion. So this topic is very important. It is the question regarding Kepler's laws. It is asked in a recent exam, that is March 2020. So Kepler's laws of planetary motion. So he stated 3 laws of the planets around, how they revolve around the sun. Okay, so the Kepler's first law is very simple. The orbit of planet is an ellipse with the sun at one of the foci. So sun is at one of the foci and the planet is revolving in which type of orbit? It is revolving in elliptical orbit. So orbit of the planet is an ellipse, it is not a circle. Okay, so this is the first law. Kepler says that the orbit of the planet is an ellipse, and in ellipse the sun is at one of the foci, it is not at the middle center. Okay, so remember this, a simple law. Now the Kepler's second law. Look at the statement. The line joining the planet and the sun sweeps equal areas in equal intervals of time. So let us see the explanation. So line joining the planet and the sun. So look at the line where the point A. So it can be a position of the planet. So let us see a point A. So line joining point A to the sun, it is sweeping the area up to line joining the sun and planet point B. This is second position of planet. Okay, so it sweeps. This is the area under the arc AB is the area covered by swept by the planet. So it sweeps equal area in equal interval of time. If we check the intervals of time, in same time it sweeps the equal areas. We can see the next animation to understand this. So look at the different positions of the planet and different lines are given, and area is shown by a different color, whitish color. Okay, so the line joining, take any position, line joining the take point A, B and C. Just take these 3 points. So the line joining, this line joining A and sun, and sweeps the equal area up to the arc. So this is the area of arc AB, and this is the area under the arc BC. So if it travels from A to B in the same time it travels B to C, if the time is same, then the area under AB and under BC are same. So the line joining the planet and the sun sweeps equal areas in equal intervals of time. This is the second law. Now Kepler's third law. The square of its period of revolution around the sun means the square of period of revolution, that is the time required for a planet to complete its one revolution. Just like for Earth, it is, we know that it is 365 days, 1 year period of revolution of Earth. So that period, it is denoted by capital T. So the square of this period of revolution, that is capital T, around the sun is directly proportional to the cube of the mean distance of planet from the sun. So T square is directly proportional to R cube. Here R is the mean distance of planet from the sun. It is not radius because the orbit is not circular, orbit is elliptical. So R is mean distance of planet from the sun, and because as the orbit is elliptical and sun is at one of the foci, the distance of the planet varies from point to point. So it is the mean distance means average, R is average distance. So T square is directly proportional to R cube, that is square of period of revolution is directly proportional to cube of mean distance of planet from the sun. Okay. So these are the 3 laws. First law is about the orbits, it is ellipse, and where sun is at one focus, one of the foci. And second law is equal areas in equal intervals of time, means the planet covers, or line joining the planet and the sun, it covers, sweeps equal areas in equal intervals of time. And third one is the relation between the period of revolution and mean distance. T square is directly proportional to r cube. So you can remember the three laws simply by first ellipse, orbit, ellipse, second equal areas in equal interval of time, and third one T square is directly proportional to r cube. Okay. Now the next concept we are going to see is center of mass. So to understand the next law, we need to understand this concept, center of mass. Now center of mass of any object is nothing but the point where all the mass is concentrated. Look at the definition. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. So where the total mass is assumed to be constant, not constant, it is assumed to be concentrated. So here this chart shows the center of mass of different objects, like the objects which have uniform density. So it can be a spherical object or it can be of any shape. For spherical object, uniform density, so density is uniform all over the object, it is considered. If the object is spherical, its center of mass will be at its geometrical center, means at its center. Okay, and for any shape of the object, it will be at its centroid. Next, this figure shows. So look at this. For spherical object, the center of mass is shown by this green, the center of mass is shown by green points. For spherical object, it is at the center. For other triangle and other objects, it is at their centroid. So center of mass is where the mass is concentrated. For circular body, it is at the center. For other bodies, it is at the centroid. Okay. Now Newton's universal law of gravitation. So Newton says that every object in the universe, attracts every other object with a definite force. This force is directly proportional to the product of masses of the two objects and is inversely proportional to the square of the distance between them. So Newton says that every object, say this m2 or m1, every object having mass, say here m1. So every object attracts every other object in the universe with a definite force, and that force, for example, here m1 is attracting m2, m2 is also attracting m1, because every object attracts every other object. Okay, so but the force is directly proportional to product of their masses. So for example, m1 is attracting m2, so the force is directly proportional to the product of the object and the object it is attracting towards itself, so m1 into m2, and it is inversely proportional to the distance, because as the distance is increased, the force is weakened, right? So force is less between the distant objects, force is more between the objects which are nearer, right? So let us formulate it. So force, F for force, is directly proportional to product of the masses of the two objects. Force is between the two objects, so force is directly proportional to product of the masses and inversely proportional to square of the distance between the objects. We can write it like this also. We can take one constant and equate it. F is equal to G m1 m2 upon d square, where G is called as universal gravitational constant. It is constant all over the universe. So next slide is about that only. So have you got Newton's universal law of gravitation? It is applied in the whole universe, where any object, every object attracts every other object with definite force, and the force is directly proportional to product of their masses and inversely proportional to the square of the distance between the objects. Okay. So universal gravitation constant, which is denoted by capital G. So we have seen this formula, right? F is equal to G m1 m2 upon d square. So we can rearrange it and write it like this, right? F is equal to G m1 m2 upon d square, and so we can write G is equal to F into d square upon m1 and 2. We just rearranged it. So it's SI unit from this formula, which is marked here. From this formula you can form its SI unit, which is Newton for force, right? Newton into distance unit is Newton for force. Let me mark it. Force, Newton for distance square means distance SI unit, meter square, then m1 into m2, so kilogram into kilogram square, right? So Newton meter square per kg square. You can also write it like Newton meter square and kilogram raised to the power minus 2. As it is in the denominator, you can write it in the numerator with negative power. Its value is universally constant, and its value is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Okay. So this is also important for objective questions. It was asked many times, the SI unit or the value. Okay. So remember it. Next point is high tide and low tide. So you must have heard about the high tides and low tides in the sea. Bharti, Ohoti, I class it, right? So high tide, that is Bharti, and low tide is Ohoti. So why do that happen, high tides and low tides? So it's the effect of gravitation of moon. As the earth is attracting moon towards itself, so it is revolving around the earth, right? Because of the gravitational force. So as earth is one object in the universe, so moon is another object in the universe. So moon also has its gravitational force. Moon also attracts the things by gravitational force. So high tide and low tide are effect of moon's gravitation. And look at the animation. You can see high tide, where the water is it is shown by blue color here. So look here, high tide. Look at the high tides, and high tide is occurred because the water level is increased towards the moon. The water level at the side of the moon is attracted, water is attracted towards the moon, therefore the water level at that point is increased, and at exactly 90 degree to that point there will be low tides, and exactly 180 degree there will also be high tide. So it occurs, high tide, low tides occur at different times at different places. So you can see this, and earth is moon is, as moon is revolving around the earth, and earth is also rotating itself. You can see both the motions, revolution of moon and rotation of earth. So therefore, because of the motions and because of the gravitation, high tide, low tide occurs because of the gravitation, and they occur at different times and different places because of the motion of the earth and the moon. Now next point is Earth's gravitational force. You can see this animation, simple. You can see the different balls, so concentrate on any ball, say red ball. So if the red ball is thrown upwards, you can see initially, or any ball, So initially the balls are having some velocity and they go upward, and the velocity is decreasing, you can see it, right? And the velocity is decreasing. At one point the velocity for instant it becomes 0 and the ball again comes downwards. So this is because of Earth's gravitation force. When we throw any object or any ball, anything upwards, so we give it some velocity. So using that velocity it tries to go upward, and it is opposite to the direction of gravitation, right? So the direction of gravitation is towards the center of the earth. We are throwing something upwards, means because using that velocity it is going in opposite direction to the gravitational force, right? So it is going in upward direction, but downward pull is, there is gravitational force by the center of the earth, so its velocity decreases because of that force. It becomes 0 at one point and it again comes back to the earth. So that is simple effect of earth's gravitational force. So why does Earth not move towards the apple? So this question, as we know that as we have seen the Newton's law of gravitation, we have seen that every object in the universe attracts every other object. So we said that apple is falling on the earth, means earth exerts force on apple. But apple is also one object in the universe, so it also exerts force on the earth, right? According to the law, it also, apple also exerts force on the earth, right? Gravitational force. So why does the earth why does earth not move towards the apple? Apple move towards the earth, but why earth not move towards the apple? So this answer is very simple. As we compare both of them, earth is too massive, mass of the earth is too high as compared to apple, right? So the apple cannot move earth. Now next question, why do the moon and artificial satellites not fall on earth like apple? We know that earth exerts gravitational force on apple, so apple falls on the earth. We have seen that, we have said that the earth also exerts pressure on gravitational force on pressure sorry pressure gravitational force on moon. So why does that moon not fall on the earth, moon or any artificial satellites? So the answer is because of their velocity along the orbit. As they have velocity, they do not fall on the, they move in along the orbit. Okay, they do not fall. But if there is no velocity, just imagine that if the moon decided to stop, he's tired now, by he is revolving for the years around the earth, he's tired now, he said that let me take some rest for some minutes, for just 1 minute or for 1 second. If it stops, it will fall down towards the earth. So because of the velocity, they are revolving, they are not falling, moon or any artificial satellite. Okay, and gravitational force is obviously there, but it acts as centripetal force for that circular motion. Now next is Earth's gravitational acceleration, that is denoted by small g. We have seen two g's here, one capital G which is universal gravitational constant, which is constant everywhere in the universe. So it is called as universal gravitational constant. Now next is Earth's gravitational acceleration. Now we are talking about Earth only. So Earth's gravitational acceleration, we have seen the concept what is acceleration. When there is change in velocity, it is called as acceleration. Change in velocity per unit time is called as acceleration, right? So what is Earth's gravitational acceleration? And remember, this is denoted by g. So in 9th standard we have seen Newton's second law of motion, and we remember it just by this formula, F is equal to ma, that is force is equal to mass into acceleration. It means that when there is some force, means there will be some change, acceleration. A force acting on a body results in its acceleration. For example, if means any force causes change in velocity, means that there is acceleration because of the force. So we have seen studied it in 9th standard. So here force is we are talking about the gravitation. So Earth's gravitation force. So the force is gravitational force. So therefore the acceleration because of that force, as there is force, gravitation force is there, and because of force there will be acceleration. So that acceleration is called as acceleration due to gravity. We are going to study it in detail in this lesson, so you will get it. But from the second law, if there is force, there is acceleration. Now here is gravitational force, means there is some acceleration, which is called as acceleration due to gravity, which is denoted by small g. It is a vector quantity. We know that acceleration is vector quantity, means it is denoted by magnitude as well as direction. And its direction is towards the center of Earth, just like the direction of the gravitation force. जशी gravitational force ची direction आहे तशी त्या acceleration ची direction आहे towards the center of, जिकडे force तिकडे acceleration towards the center of Earth. Let us see the derivation of the formula. Earth's gravitational acceleration. It is very simple. So look at the diagram where the black line, one object is shown above the Earth. So from the center of, we are taking the distances from the center of the Earth, not from the surface of the Earth. From center of the Earth, its distance is small r. Right, so distance between the Earth and the object is r, right? And we have seen the from universal law of gravitation that the F is equal to, the force between the object and the Earth is equal to GMM. So M, capital M is mass of this Earth, capital M is mass of the Earth, and small m is mass of the object. So, and distance between them is r. So GMM upon r square. Here we have not taken M1, M2. We have taken capital M and small m. But from the Newton's second law of motion, we have seen that F is equal to ma, just like in previous slide. But here acceleration is gravitational acceleration. So F is equal to ma becomes F is equal to mg. Just a is replaced by g because here it is gravitational acceleration. So here F is equal to mg. F is equal to ma becomes F is equal to mg. So F is equal to gmm upon r square is the first equation, right? Then F is equal to mg is the second equation. So we can equate both of them and we will get mg is equal to gmm upon r square. So this m get cancelled and we get small g is equal to gm upon r square. So g is gravitational constant, m is mass of the Earth, which is also known, and r is the distance of object from the center. If it is known from this distance, and at the for the object which is on the Earth, which is on the Earth's surface, say here, so the distance will be just radius of the Earth, right? So the value of g at the surface of the Earth is around, g is equal to 9.77 meter per second square. So here unit is meter per second square because this is acceleration and we know the unit of acceleration is meter per second square, right? So Earth's gravitational acceleration, from the previous slide we have seen it that if there is gravitational force, there is gravitational acceleration, which is denoted by small g. It is a vector quantity, it is directed towards the center of Earth, right? And now we have derived it, small g is equal to capital G capital M upon r square. So g is equal to gravitation constant into mass of earth upon r square means the distance of the object from center of earth. Now this G, as we have seen that universal constant capital G is constant everywhere on the in universe. So on the earth also it is constant, everywhere it is constant, but this small g, that gravitation, that's gravitational acceleration, it is variable along the surface of the earth, or in many places it is different. So let us see the variation in value of g. So under that, the first point is change along the surface of earth, or at any points on the earth surface, how will be the value of g. So let us see these points, let us see this diagram. So because of the continuous rotations and revolutions for many million and billion of years, so shape of the earth has been somewhat changed. So the shape is has become like this. The earth is flat at the poles and it is bulged at the equators. So you can see this from the diagram, right? So as earth is flat from the poles and it is bulged at the equators, means from the center of the earth, the distance, it is not completely spherical, so the distance from the poles, distance of center means this radius or distance of this point, where it is flat from the center, and distance of this point, that is where it is bulged from the center, they are different, right? So as the different distance changes, g's value changes, because g is equal to gm upon capital Gm upon r square. So as the radius is changed, or as the distance of the object from the center is changed, the values can be different, right? So where that, as the formula is g is equal to gm upon r square, so it is inversely proportional to the distance square. So as the distance is less, here the distance is less because the earth is flattened and at the equator it is bulged, so the distance from the center is more. So where the distance is less, value will be the highest because it is in inverse proportion with the distance. So it is highest at the poles and lowest at the equators. So here highest value and here lowest value, and the in between values varies from this 9.832 highest value to and between 9.78 meter per second square. So that difference is not big enough, but there is. So now the next variation is variation with height. We have seen the value of g at different points on the earth. Now how does it change with the height above the earth? Now consider this diagram. So this is center of earth, capital R is radius of earth, and the distance from surfaces take as h. So the total distance of center to the object is this capital R plus h, and which is actually taken as small r. We have already taken as small r the distance of object from the center, small r, and we have seen this formula gm upon r square. So as the r increases with the height, r increases, right? So distance increases, so as small r increases and r is in inverse proportion, g obviously decreases. But this change is negligible for smaller height, as we know that r, the radius of earth is 6,400 kilometers. So this much is the radius of the earth. So we go above 10 kilometer, means the change is very much smaller as compared to the center, right? as compared to the radius. So just for some heights like from earth surface, that is 10 kilometer, 20, 100, there will not be the change in the value of g will be very negligible for smaller height. So 10 kilometer, though the height 10 kilometer or 20 kilometer, 50 kilometer is very much very high for us, but actually as compared to the center of the earth or a radius of the earth, it is very much smaller. So the value is variation in g is negligible for smaller heights from the earth's surface as compared to radius of the earth. So there is a lot change when the height becomes the object goes to what we can say in thousands kilometers. Okay, so as r decreases above the earth's surface or the object goes high, r increases, right? The distance increases from the center, so the g decreases. Gravitational acceleration, value of gravitational acceleration. Next is variation value of g with change with depth. So we have seen on the surface, we have seen with the height. Now let us see with the depth inside the earth. So as we go inside the earth, look at this. As we go inside the earth, obviously the distance from the center will be decreased. So r, sorry, here there should be r decreases, right? So this is correction. So as r decreases, we should think that g should increase as they are in inverse relation. So r decreases, distance decreases towards the center, distance decreases, but the mass, the part of the earth which is part of the earth see this, if we are going inside the earth, the part of the earth which is considered means the mass also get decreased. If we are standing here, the mass is considered, or the whole mass is considered. If we are standing here, the whole mass is considered, right? If we go inside the earth, so here the distance from the center is decreased, but the mass part of the earth we are considering is also decreasing. So mass is also decreasing. So as mass decreases, g also decreases. So the total effect, r is decreasing, g is also m is also decreasing. So total effect causes that gravitational acceleration's value inside the earth also decreases, and at the center of the earth, as r is 0, mass is 0, it becomes 0. The g's value at the center of the earth is 0. Getting it? So the highest value of earth's gravitational acceleration is on the surface of the earth, and that too on the poles. That is, we have seen 9.832 meter per second square, right? So as we go above the height, as we go with the height, the g decreases. In the depth, g decreases, and at the surface it is highest. Okay.